Okay. Highly esteemed keynote speaker of this webinar, Dr.g Ramanamurthy garu, respected Principal Dr. R.V. Krsihnaiah garu, Honorable Director Professor N. Venkatrao garu, HOD of ECE Department Dr. N. Vijay Shankar garu, and participants from various reputed institutions across the country. A warm and graceful afternoon to everyone. It's my immense pleasure and great honor to welcome you all on behalf of Chebrolu Engineering College to this webinar on future trends in CMOS technology at 5 nanometers and beyond, which is being organized by the Department of Electronics and Communication Engineering. I must mention our deep sense of appreciation to the convener, Professor K. Manoj Pavan Kumar, and the organizing committee who toiled hard and contributed with their thoughts in organizing this program. We are very grateful to the speaker for his kind acceptance and precious time. We assure you that he will kindle the fire of enthusiasm in all of us. I deem it great privilege to introduce the keynote speaker of this webinar, Dr. Gajula Ramanamurthy garu. He is a towering personality and a fountainhead of knowledge. He has been associated with the Faculty of Engineering and Technology, Multimedia University, Malaysia since 2005. Currently, Dr. Murthy is rendering his services as a professor in that institute. He has authored and co-authored several national and international publications and is also working as a reviewer for reputed professional journals. Dr. Murthy is actively associated with different societies and academies around the world. He made his mark in the scientific community with his invaluable contributions, gained wide recognition from honorable subject experts around the world. Dr. Murthy has received several awards for his contribution to the scientific community. His research interest involves engineering and technology. On behalf of Chebrolu Engineering College, we cordially welcome Dr. Ramanamurthy garu to offer insight into the topic of today's webinar, Future Trends in CMOS Technology at 5 nanometers and beyond. It's over to you, sir.
Thank you so much. First of all, I would like to take this opportunity to show my gratefulness to meet all of you and would like to take candidates in place of the conventional MOSFET design, along with certain software simulation as well. As you know very well, in today's fab technology, going for any particular node technology to design a fab-based design is quite expensive. Thereby, today's researchers mainly focus on simulation-based before they go for any fab design. Well, where is the CMOS today as such? Right now, we have a 14 nanometer commercially available technology node available, and we are moving down towards 10 nanometers, 7 nanometers, and then right now, one is there are two companies already successfully implemented 5 nanometers. One is TSMC, that is Taiwan's semiconductor manufacturing company. The other one is Samsung, our mobile company, the cellular company, the Samsung. These two companies have already successfully implemented, but it's not been commercialized yet. So right now the technology is revolving around 5 nanometers. Even though it shows 5 nanometers, the effective length is actually 10 to 12 nanometers. The reason behind that is the unit for any design is approximated to 2 lambda, where lambda is your gate length. So the 5 nanometers, what we are representing here is with respect to the gate length, and the design unit is 2 lambda, thereby it's actually 10 to 12 effective length of your design. As we begin work on the 5 nanometer node, is there a new device technology we should be seriously looking at it? That is the problem and the question arising in many researchers' mind as of today. And we are going to have a detailed outlook like what kind of device alternatives that one researcher can really focus into. And it has gone beyond a simple electronics engineer now. It has gone to various research fields, and it's a combination of nanoscience, nanotechnology, VLSI design, digital design, even the physical expertise, all these kinds of expertise. It has become a teamwork at the moment, As we move through the slides, it would be clearly evident. Like, what are the challenges we are going to face as a researcher at 5 nanometers node is what is main problem of concern for the researchers, isn't it? So there are a few highlighted here. The first one is electrostatics. Then we all know the parasitics, the parasitic capacitances that arise at every junction, at every PN junction in your semiconductor device. And leakages are popping up as your technology is shrinking. Now the conventional MOSFET design has become obsolete below 20 nanometer, as all of us already know that. Now beyond 20 nanometers, researchers have been moved out of the conventional FET device, and they're looking for the replacement candidates. And then we are going to see some of those replacement candidates in place of a conventional CMOS design. Like low voltage operation, when you are scaling down to 5 nanometer and even beyond that, I think the futuristic node, technology node has become, I think is 3 nanometers, but that is in future. At the moment, the technology is revolving around 5 nanometer node. What performance, like VDD is actually the supply voltage. The supply voltage has become now 0.5 volts. Earlier, when we were introduced digital electronics, we were taught that 5 volts is considered as 1, digital logic 1, and 0 volts is considered as digital logic 0. That was the trend we started from TTL onwards, isn't it? So now that 5 volts has come down to 0.5 volts. So VDD 0.5 volts means 0.5 volts level is considered as digital logic 1 now. And now, of course, digital logic 0 is still remains at 0 volts. So now the difference between logic 1 and 0 is absolutely only 0.5 volts. In such case, what kind of devices you should be really looking into to fulfill your performance and your requirements and all those things, okay? So how does the device works when you're giving 0.5 volts as your VDD? How does it works? And why is it promising? You know, like a conventional FET doesn't function anymore beyond 20 nanometer node. Then how about the other devices they are promising for us? And what kinds of trade-offs we should be really looking into while focusing on certain design parameters? And where do we actually stand at the moment? And this webinar actually, several researchers, active researchers in this field, their contributions have been taken. The reason beyond that is, in order to benchmark any new outcome being a researcher, you must have certain well-renowned researchers work as benchmark, isn't it? So in order to make that visible, several renowned personalities output is considered as benchmark throughout the world. So those findings are shown in this. Well, coming to the low voltage now. As I said now, 0.5 volts has become the logic 1 at 5 nanometer technology, right? So when you're talking about low voltage, what kinds of challenges we are going to face? Okay, now as you see here, I on is the on current when your device is turned on, right? And when we are, this is actually happening when we see on, this is a volt ampere characteristic curve of a normal conventional FET device, where VDS, that is the voltage between the drain and source, is taken on x-axis, and a logarithmic plot of the drain current is taken on y-axis. So when you're plotting a graph like this, we could easily see that this is VT. VT is our threshold voltage. The device runs in a normal mode after the threshold voltage, meaning to say that your conventional FET turns on beyond threshold voltage, because threshold voltage is the voltage where it nullifies and it develops your inversion layer and your carrier starts moving from source to drain. Then sometimes researchers are quite interested even below VT. That is what we call it a sub-threshold current and sub-threshold region. Because once, if you closely observe, device doesn't turn off all of a sudden from an on state, isn't it? So this is where we are talking about an on state, where we are talking about I on, and this is where we are now talking about an off state, the true extreme ends of your curve. So in the process, the device doesn't turn off all of a sudden, right? So as we can see from the graph, there is certain amount of current that is still available in the device, and we call this current as sub-threshold current, or we call this as leakage current. And some researchers focus on why can't this amount of current actually turn on our devices, and then they start focusing the research within this stipulated area itself. So they call it a sub-threshold region. Many researchers explore the possibilities of research in this area itself, and we call that as a sub-threshold region. And now, the slope of this curve is called as sub-threshold slope, and greater than 60 millivolts per decade has become a nominal figure. The reason behind that is because of the limitation of the thermal voltage. Okay, thermal voltage Vt is Boltzmann constant K times K by Q, right? So in this K Q by V, this is temperature T by Q. So the temperature and Q are constants. It doesn't change with respect to your technology node. And whereas Boltzmann's constant K is also a constant parameter. So thereby we have a limitation on thermal voltage. We would not be able to generate beyond that. So 60 millivolts per decade has become a nominal parameter. Beyond that, you know, your circuit does not produce carriers beyond that. Good. Now we move on to the next approaches. Okay, what kind of approaches are quite appropriate in this low voltage region? So we know very well that we wanted to move below 60 millivolts per decade if possible, which is not the case in case of a conventional MOSFET. And if there is any other devices which can fulfill this requirement, then obviously researchers are more intended to focus on those lines. As you see there, the black curve is a normal conventional MOSFETs, and the red one is, we are talking about 3-5 FETs. What is this 3-5? Now, many researchers who are known in this field, they know very well. It's actually, we are now taking the elements from group 3 and group 5 from your periodic table, and these components, a combination of these elements are used in place of silicon, conventional silicon, in designing FETs. So thereby we call them as 3-5 category of FETs. Some of them are like nanowired FETs, and even in some cases BJTs are all aptly used. It's not that BJTs we wanted to use in place of an FET, but as we run through the slides, we would know there is a physical presence automatically of a BJT inside the device structure. Then the blue option is more optimum compared to all the three curves, and this is the outcome of an internal gain. We call them as IFET. IFET stands for internal gain FETs, and we see some of those examples in today's seminar, as well as TFETs like tunneling field effect transistors. So as you see, if you are looking mainly for subthreshold slope, the promising candidate is obviously internal gain FETs and TFETs. So like that, we cannot say that one particular design is, you know, renowned because you have your trade-offs. I want more S's, then maybe TFET is not the right candidate. So like that, depending upon our design requirements, you need to go for various trade-offs between parameters. Okay, well, right now, let us have a recap, because sometimes I do understand that all the participants may not be well versed in this field. So I thought a last minute inclusion of these slides, like short channel effects. What all the short channel effects, and which actually, if you ask me, short channel effects is considered as a research gap, because whenever being a researcher you wanted to explore in a new expertise or new field in a well-defined VLSI or well-defined devices or well-defined simulations, first of all, where we focus is the research gap, where actually we can contribute, isn't it? So right now, if you focus on short channel effects of MOSFET devices, you would be coming across several research gaps. and one can actually pick from one of these gaps, and from there he can intend to develop his research and then try to contribute to the society. So some of the well-known short channel effects are highlighted here is ID is not linear anymore. Linear in the sense it's quadratically expressed in terms of mathematical expression earlier, and that is with respect to the gate voltage, and this does not fulfill anymore. Meaning to say, our conventional drift diffusion model fails when you are looking into short channel effects. Thereby, the new terms are coming in, like we call it as earlier, whatever the mathematical models using BSIM, Berkeley simulation models we have been using, all are based on conventional drift diffusion models. Now, quasi models are available, ballistic models are available, like the different kinds of models are available because we are now considering quantum mechanical effects as well in your models. And then apart from classical models, we incorporate even quantum mechanical confinement models are also incorporated inside. Then high voltage conductance. This is actually not a welcoming parameter. So your conductance, high output conductance actually easily can drive the other impact of other neighboring circuits, isn't it? So we must always have a high output impedance, thereby your circuit doesn't affect with other neighboring circuit parameters like fan in and fan out. Then threshold voltage roll-off. Threshold voltage roll-off is one of the prominent feature which is arising because of our short circuit channel effects, and your threshold voltage no more is going to be a constant as it was the case in long channels, and it varies with different parameters. And what are the parameters we are going to run through? Then increased DABL. DABL means drain induced barrier lowering. So we all know very well, under normal circumstances, when a carrier is moving from source to the drain, it has to cross certain electronic, certain inbuilt energy barrier, isn't it? That's a Fermi barrier. Now, what happens is the gate voltage controls usually the barrier levels. At certain level, that is your threshold level, when gate voltage level comes to your threshold level, automatically this energy barrier level is nullified and your carrier is actually moving from source to the drain. This is what actually our intention while designing any MOSFET. But now, because the channel is reduced and we are now calling it as a short channel, the voltage at the drain also reduces the potential barrier. So thereby, slowly the gate is losing control over the carrier movement, which is not a welcoming parameter, right? So increasing DABL means when your DABL is increasing, your gate is obviously losing control over the carrier moments. Then increased SS is actually SS, subthreshold slope. If the subthreshold slope is increasing, then your design doesn't turn off automatically from an on state, and it consumes a lot of leakage currents. Then the other one is a punch through, okay? And each one we see maybe quickly details. This is the thing I'm talking about. Under a long channel, when we see the volt ampere characteristic curve of a conventional MOSFET, it follows a certain conventional mathematical formula, right? A square law is implemented. So you see thereby your current gets almost saturated towards the higher end of your drain source voltages. Similarly, low output conductance. These are the desired parameters in long channel and welcoming parameters, which we are going to miss when we move to a short channel. So thereby you see the drain current doesn't stagnate anymore. It actually exceeds certain level, okay? And it doesn't follow anymore the normal conventional mathematical formula. Same is the case now. You see the high output conductance. Obviously, the output current increases. It obviously contributes the output conductance as well. Thereby, your output conductance also increases. And these two are actually not welcoming parameters in short channels. Okay, the next one is channel length modulation. Most of us have heard about this name, channel length modulation. Now we know very well, this is a conventional bulk FET device where we have the blue colored one is the substrate, and we have a source terminal here, and we have a drain terminal here, and this is our gate. And this gate is actually, we implant the gate through a insulator. Okay, SiO2, silicon dioxide, is a conventional insulator used. Now what happens is, if this gate length is becoming less and less, like I said, now 5 nanometer is the current technology, right? So the gate length here is 5 nanometer. So the channel length is reduced. The minute the channel length is reduced, automatically your gate voltage is also reduced because they are directly proportional. Thereby, your threshold voltage level is reduced and your VDD is also reduced. So these are all interconnected. So now, this is the normal practice. Now, instead of this, if this somehow this channel length is reduced without our intention, that problem is considered as channel length modulation, because this internal length further deteriorates our threshold voltage, further deteriorates our VDD, which are not actually intended as per our design, right? So now the voltage level at the drain is the main cause for a punch through or pinch off region moving closer and closer, right? Thereby your channel length is further reduced. A high voltage at the drain makes your pinch off penetrates deeper into the gate, thereby reducing the length of the gate, thereby reducing threshold voltage. Meaning to say, we do not have a predetermined control of the threshold voltage because of the high voltage at the drain. So now channel, since it's reduced, so you see the drain current is actually the mobility of the affected carriers and oxide thickness with respect to the width and the length. Length is the effective length of your channel, and suppose VGS minus VT is the threshold voltage. So this is a conventional formula valid even for short regions. This is applicable when VGS is greater than the threshold, as well as VDS is in between that of the VGS and VT. Now, when the channel is becoming too short, now no more we call it as it's been controlled by only the VDS. Now you see on y-axis we see the VDS. That is what we call it as voltage connected between the drain and the source. And X, there is one more coming here, right? That is your gate voltage. Okay, now you can ask one question. Why is it that gate voltage was also there earlier, right? Now why you are calling it as like a two-dimensional fields, you know? As the channel is becoming lower and lower and reduced to a short channel level, then your gate level also has a predominant effect on the movement of your carriers. That's why it has become two-dimensional when you're reducing the channel length. Okay, one more short channel effects is VT roll-off. As I said earlier, your threshold voltage is actually reduced by a certain parameter, right? So the delta VT is actually called as VT roll-off. How much it's been reduced, and what is the physical relationship between the amount of the gate voltage as well as your channel length. So we have a conventional methods, and a lot of research is done under this area. Okay, now if you see, the red line is actually the one going down, and this is a conventional threshold voltage roll-off curve. So how about this one, the dotted one? This is named as reverse short channel effect. What is suddenly why a new thing is coming in, a reverse short channel effect? Reverse short channel effect is actually coming because of hollow doping. What is the hollow doping? Hollow doping is actually in certain advanced devices, what they do is they vary the doping levels at the source, at the channel, at the drain levels. So they increase high-end doping at source as well as high-end doping at the drain compared to the channel as such. So that causes your depletion layer at the drain end deeply penetrates now because of the higher doping, and sometimes it may even touch your source. Thereby, certain voltages are internally developed at the substrate level itself. So this voltage opposes your conventional gate voltage. Thereby, to turn on the inversion layer, your gate level voltage should be higher. So that is what is actually reverse short channel effects. So when people are going for one kind of research, unnecessarily they are coming up with unknowing side effects. So reverse short channel effect is one of the side effects of your hollow doping technologies. And like I already discussed, drain-induced barrier lowering, right? So whenever your voltage at the drain is becoming higher and higher, then obviously it reduces the energy band diagram apart from the gate. So and slowly the gate is losing control over the carrier movement from source to the drain. So this is usually in the order of millivolts per volt, and it has on a conventional curve we can actually see when VDS is 0.1 volt, so this is the curve, and VDS is 0.05 volts, this is the curve. And if they are looking like a linear relationship, there is no big issue. They don't become linear at some stage. This is where your short channel effects are becoming more stronger, and it doesn't follow any linear relationships. And this is even severe, right? So like that. And this may be the reason of a punch through. Okay, punch through means, what is a punch through? Okay, maybe we see that. Sometimes because of excess lateral field strength. No, now we are calling them as two terms. Okay, one is a coaxial electric field and lateral electric field, or you can say conventional x direction and conventional y direction. X direction is actually the voltage applied between the drain and source, VDS, and lateral field is your VGS, between gate and the substrate. Now, since the length of the gate is reduced earlier, even though there was a VGS, it was not affecting any carrier movement from source to the drain. Now, since the gate is reduced, length of the gate is reduced and it's becoming short channel, now the impact of this gate voltage and the movement of the carriers is also coming into consideration. Now they get surface scattering. Now what happens is excess voltage, positive voltage at the gate, your electrons are getting attracted, and then this, instead of moving straight away from source to the drain, they get collided with the surface of SiO2 interface. So we call this phenomenon as surface scattering. Due to the surface scattering, a high mobile carriers get surface scattering at the surface of SiO2 interface. The carriers reaching at the drain end automatically minimizes. So punch through is not actually that. The one I'm talking about is the surface scattering. Punch through is like high mobile carrier now punches through the barrier. It doesn't actually wait for the gate applied voltage and then gain energy and then cross the barrier. It actually has a high energy because of the lateral field, and it punches to the barrier. So thereby you have additional amount of carriers reaching the drain region. That is actually the punch through concept. It punches to the barrier because of the excess lateral fields. Okay, what kind of simulation models right now available for any researchers to do a benchmarking, right? So I'm considering like one of the well-renowned MIT VS, and in short we call it as MVS model. This model is quite renowned, and if you are starting in this area, I do recommend you to use this model as your benchmark model. If your design comes beyond any one of the, say for example, better results than this existing model, then you can obviously consider your work is quite predominant and you can go straight away for publication. A simple MIT, of course, all of us know this Massachusetts Institute of Technology, and VS is stands for Virtual Source transportation model. And they have, and it's actually, you can download that, it's a freeware. And now actually they have even a third version, MES3 model is available. And this includes FD Fermi-Dirac statistics and non-parabolicity are all included, and quasi quantum mechanical models are incorporated. As I said now, simple drift diffusion models have become obsolete now. People are moving for either quasi quantum models or complete quantum models. Complete quantum models are not actually well versed with technocrats like us, so thereby we use still classic mechanics with quantum mechanical confinements adoption. So improved capacitance model, that is due to quantum effects. Then semi-empirical electrostatics. So this is what I'm telling, like quasi-quantum mechanical effects. Then predicts injection velocity. Complete IV characteristics are ready-made available as a benchmark. From M star may be a new term for some of us. This is what is actually the electron mobility, okay? Mobility of the weight of the electron. Then mobility, then L effective, actual length, effective length of the gate, and degeneration. Sometimes they degenerate, meaning to say what is degeneration? Before the carrier moves from the source to the destination, some of them may recombine due to excess holes in the device, in the substrate. That leads to degeneration. Okay, so this is where we can actually download the MITVS models. Now the current version I checked the other day was model 3 is available. That is still applicable for 5 nanometer device technology. And our research can be benchmarked with the conventional worldwide recognized bench models from these nano hub. We can compare from there, thereby you know at what level actually our research is actually heading to. And if I sincerely suggest, if your findings are somewhere on par or somewhere below than findings of this, then obviously our work is not that pronounced, and then I think we should do some more additional work to extend. Okay, we have quickly glanced through some of the short channel effects, right? So these are the research gaps. Someone focuses right now on only sub-threshold slope. Somebody focuses only on threshold voltage roll-off. Somebody focuses only upon output conductance. So focusing on all these parameters is absolutely not possible, because bottleneck, you actually try to trade off between certain parameters and improve on certain parameters. I don't mind having additional sub-threshold slope at the expense of some other parameter, so at the gain of some other parameter, and so on. Okay, so now low voltage silicon benchmark. So that's what now we are going to go through in some slides. The conventional 14 nanometer FinFET technology output results are shown here from some researchers. Dr.g is one Indian as well. So we can see the 14 nanometer CMOS FinFET technology output with respect to your VDS as well as drain current for both, because it looks like a replica, isn't it? Because one end is the PMOS, another end is the NMOS. So if you don't want to visualize on PMOS, we can only focus on the right hand side of the graph. Same is the case here also, VGS with respect to the drain current for NMOS as well as PMOS. So these are the conventional benchmark results if you are working on FinFET. Okay, so what do you do? No, I'm talking about suddenly into a FinFET, right? FinFET is no more a planar device, it's actually a vertical platform, right? So now if you are working on a planar device platform, then can I still use these conventional benchmark models to assess my work? Yes, it can be done. So they have given one method for that. Map the FinFET to an equivalent planar structure, then divide measure current per micron by 2, because that is vertical structure, right? Then fit the 14 nanometer Intel data with a planar model, then actually you can start benchmarking your models. Okay. And those models are shown here. This is after converting FinFET model to a planar model. I'm designing a planar structure. I'm not going for a FinFET design, but still I can use this MES model data as my benchmark data. And then if I could design a device which shows a better performance compared to these benchmark models, then I can right away say that our device is much better than the some of these findings. Okay, so the EOD is actually the equivalent oxide thickness, and L effective length is the gate length, subthreshold swing, some standard values are given, because when you're simulating your device, the device will ask you to input with certain parameters, right? So these are the parameter values input before the simulation gives you the output waveforms like this. So thereby these parameters are already listed out. If you say if EOD is 0.8 nanometer, I had a better result, then your benchmarking is not right. So you need to go with the same kind of key parameters before you use a benchmark results. So thereby effective mobility is also shown, then MT. Okay, now the weight, right? Carrier weight. M stands for the carrier weight. Carrier weight is also defined into two. One is transverse, that is on vertical field, as well as another one is the longitudinal on horizontal axis. And they are the conventional formulas like 0.19 m0 and 0.8 m0. This is taken from the silicon structure, okay? Three-dimensional silicon structure. In a three-dimensional silicon structure, basically the third dimension ML1 and ML2, ML1 and ML2 are equal in a silicon structure. Therefore, we have only a two-dimensional MT, traverse and vertical line, I mean on y-axis and on x-axis. So the effective mass, actually, it's a carrier moving means what? Your mass, electron mass is moving. That is the movement of the mass, isn't it? So when the mass is moving, it's not only moving in one direction on x-axis like earlier where we are talking about a long channel. So it's actually moving in both the directions, x as well as y-axis. So that's why the M is further divided into two parts like MT as well as ML. Traverse on vertical axis as well as on horizontal line. Some more results on that. Benchmark LV, low voltage, high performance silicon N MOSFET, focusing on the N MOSFET alone. So if I'm not working on a FinFET, I'm working only on a conventional N MOSFET using conventional silicon. And if your technology goes until 20 nanometer, because as I said, a conventional silicon MOSFET ceases to function beyond 20 nanometer. If you're talking about 14 nanometer, obviously our silicon planar silicon model doesn't function anymore because your drift diffusion model becomes obsolete. So you need to move on to either quasi quantum mechanical effects or completely ballistic, quasi ballistic or completely ballistic approach transport. Okay, that is where we are now showing the 20 nanometer model here, again with the same benchmark. I can what do you say, conformably say that research on a conventional planar N MOSFET has almost come to an end. Okay, so if you are looking into that line, then that's not the right path because the research has already ceased in that line, meaning to say nobody is now doing a conventional CMOS design using a N MOSFET planar devices no more because it has ceased beyond 20 nanometer level. That's what even our sometimes it's good to go for IDRS or even IRTS. Okay, and IRTS is also has become obsolete beyond 2016. Now IRDS, International Roadmap for Devices and Systems. Earlier they used to call it as International Roadmap for Semiconductors, and that is obsolete after 2016. And we have new name. Okay, a lot of researchers from academic institutions and industries, they come up with new findings and they have a protocol. Okay, and again EOT is 20 nanometers. As I said, silicon nano N MOSFET means your minimum gate length should be 20 nanometers. And this data can be used as a benchmark for our findings, research findings, and can actually check on that. That's a conventional silicon N MOSFET. Okay, now we are moving at, as I said, 20 nanometer means you said conventional silicon N MOSFET is not available. Then what are the other possibilities where the researchers must focus into beyond 20 nanometers is high channel. One of the candidate is high channel mobility MOSFETs. Another candidate is nanowire FETs. Another candidate is internal gain FETs. Another candidate is TFETs. Then the last but not the least one is 2D channel materials. Okay, these are all the promising candidates in place of a conventional MOSFET. Okay, we go one by one into a brief details. Okay, now it's the time to move into atomic table, group 3 and group 5 MOSFETs. No more simple silicon and simple germanium, right? So some recent results shows a better achievements compared to a conventional silicon and germanium by moving into the 3-5 group from the periodic table elements, combination of these group 3 and group 5 elements. And some findings are shown here, and these outputs are shown at 25 nanometers and 80 nanometers, because we should be able to say my device works very well only at the short channel. That's not our aim, right? The outcome should also work as at the long channel level, again at the short channel level. So thereby the findings are shown even at the higher end, 25 nanometers and 80 nanometers as well. First, make sure that your device functions at the long channel platform, and then you move to the short channel platform, and then see that the short channel effects are not that predominant in our design. Not necessarily to be all the short channel effects, maybe some of them, by trade off with some other parameters. That is the idea of the current researcher at the moment. Okay, so the reason why we are moving to the group 3 and 5 in a periodic table MOSFETs compared to the conventional silicon and germanium is, as you see here, the mobility is good. You have a high mobility, okay, then high injection velocity as well. When you start giving, what do you mean by injection velocity? A new term, isn't it? Earlier we used to call it as a drift velocity because of the voltage given by the gate or voltage given from the drain and source terminals. That is what is called the drift velocity. Now, the voltage given at the gate is actually injects additional carriers into the channel. Thereby, it injects additional velocity into the channel. So we call a new term as injection velocity now. Okay, this happens with small m. If the mass of your carrier is quite heavy, then injection velocity may not be that predominant anymore. So by looking at the small mass, you are able to move a little bit mass and thereby injecting injection velocity. This happens at near ballistic performance. Okay, now I would like to give a simple explanation on this ballistic performance, as this term is maybe relatively new to some of us. Okay, when we are seeing a movement of the carrier from the source to the drain, then what happens is we assume that the carrier is moving in a straight line, correct? When the carrier is moving from the source to the drain, carrier in the sense your electron is moving from the source to the drain in a straight line. This movement is what is we wanted, right? So that is what is called ballistic performance. But is it happening in reality? To some extent can say, can assume, not in fact can say, can assume it's happening in a long channel, but definitely not in a short channel, because as I said, surface scattering is happening because of the lateral field, because of the field applied at the gate, right? Your electron is getting attracted by the excess positive gate voltage and it gets collided with the silicon SiO2 interface. And this is what is called collisions happening, right? And if your carrier, before going to the drain, how many times it's getting collided with the surface. That amount is getting degradation, right? Mobility degradation. Now, the carrier movement before colliding with the boundaries is a new term is called mean free path time of your carrier. What is the mean free path time of your carrier? Means my carrier mean free path time is like 2, means it gets collided 2 times. It's 3, you say it gets collided 3 times. 3 nanometer, within the 3 nanometer range it gets collided. So that's how we start calling more into the physical terms now. So near ballistic performance is my carrier is without getting scattering, it reaches to the destination. That's what is more predominant in 3-5 MOSFETs compared to the conventional MOSFETs. And then what are the trade-offs at the expense of what you are achieving all these things? One is low DOS. DOS means density of states, and gate capacitance is also reduced to some extent. Okay, if gate capacitance, we are now talking about parasitic capacitances, right? Parasitic capacitance are negative effects, whereas gate capacitance is positive effect. Why? Because the more the gate capacitance, the faster you have an inversion layer formation at the channel, right? So thereby, which is essential parameter. So gate capacitance should be high in order to turn your device into inversion layer, and your channel turns on very quickly, thereby reducing your threshold voltage. Except gate capacitance, remaining all other capacitance are classified as parasitic. Okay, except gate capacitance, all other capacitors in your FET are classified as parasitics. They are not meaning to say contributing to our performance. So you are at the expense of gate capacitance, you are able to achieve these parameters. Okay, coming to the DOS, we never heard this term earlier because we were using drift diffusion models to simulate our conventional MOSFETs. But when the minute you incorporate quantum mechanical models, the density of states are considered to be uniform throughout the channel region in drift diffusion models, which is not the case in reality. The density of states gets, as the distance from the channel to the surface of the silicon and silicon SiO2 interface, the density of the states actually getting reduced. The carriers are not widely distributed like how at the center of the channel, the edges. Okay, that's what I mean to say. So that is what is the reason when you talk about the conventional, quantum mechanical effects means you are talking into more reality. When I'm talking about drift diffusion model means I'm assuming the carriers are uniform throughout the channel. I don't consider they are low at the edges, meaning to say at the interface, which is the reality is actually low. Then tunneling. Tunneling is a good parameter as well as bad. It depends on how you are looking into. When I'm talking about, say, gate tunneling, meaning to say the electrons are tunneling through the gate because of the thickness of the oxide is too small, then that tunneling is actually not the needed tunneling. But if the carrier is tunneling from the valence band of the source to the conduction band of the intrinsic material and it's reaching the drain, means the tunneling is the needed tunneling. So it depends on what kind of tunneling we're talking about. Then source starvation is another trade-off. With these trade-offs, your 3-5 group elements, MOSFETs, actually gain high mobility, high injection velocity, and near ballistic performance. And we have conventional. I do not go too much of into mathematics because sometimes that may not be appropriate with the given participants. So we have mobility and injection velocities already defined with these 3-5 families for 20 nanometers. Okay, now as you see here, of course, most of us with minimum background can easily understand these things. But coming here, MFP means, as I said now, mean free paths, right? Mean free paths. Now 2 means at least 2 times for a 20 nanometer gate length, your carrier gets collided 2 times before it reaches to the drain. destination. So that's what it indicates. Okay, that is what is happening in silicon, whereas indium arsenide, that is what I'm talking about, the 3-5 table, right? See the MFPs here, to what extent it's minimized. So meaning to say approximately 0.1. The possibility of getting is out of 100 is only 1. So almost near ballistic operation. So the surface scattering is not happening. The carrier is not getting collided with the boundaries, like which is the case at least 2 times in case of a silicon conventional CMOS device. Whereas here, if instead of silicon, if I'm using indium arsenide at 3.5, then I'm able to minimize the collisions, and almost it's becoming near ballistic operation. And we see the curve, okay, also increasing bonds of ballistic mobility. So your improvement also can be shown, and it's already, the research is already done in this line as well. With 3.5 is also no more prominent now. Okay, earlier to some extent, yes, conventional MOSFET moved straight away into a group 3, group 5 was the stage. And up to 40 nanometers, even 10 nanometers, they were promising candidates. Okay, certain bottleneck. Now what's happening here? Bottleneck DOS, as I said, the DOS, density of states bottleneck, right? So the density of states bottleneck is actually overcome with few layers of gates. And now, when we are thinking about a conventional MOSFET, we have only one gate, right? So now, different layers of gates, and maybe some of our researchers would have heard the name heterogate. Heterogate means they usually have 2, types of gates in one layer itself. Maybe the one is 3.5, another one is a conventional SiO2, another one is by using gallium arsenide. So 2 layers of gates are formed. So different operations of this gate. So all these changes we wanted to take place only at the end of the source terminal. So they have a 3.5 element as an insulator at the source end, and a conventional SiO2 towards the gate end. So this type of gate is called a conventional gate. So meaning to say, across the length of the gate, different materials are used as insulators. But here what we are seeing is, this is the next level. In simulations, what we are trying to do is different layers of gates are deposited. So EOT, as I said, equivalent oxide thickness up to 0.0 nanometer. I have one insulator using SA and SS35, and maybe here I have another conventional. Thereby I improve the gate capacitance. Like I already said, gate capacitance higher the better, okay? Except the gate capacitance, remaining all other capacitance are considered as parasitics in a conventional MOSFET. And some benchmarks, again by using that. For 3.5, last time we have seen the conventional benchmark from one renowned researchers for a conventional MOSFET. Now we are seeing for 3.5 materials. So the 3.5 silicon is somewhere blue, and 3.5 is the, you can see the improvement, right? So instead of using a conventional germanium and silicon to manufacture your MOSFET, in designing your MOSFET, if you go to 3.5 materials, a combination of this, then your performance obviously improves. And as I said, your off current is not 0. So obviously you improve on certain parameters, you're popping up with some unnecessary, unwanted parameters as well. But in the order of pickup amperes is actually negligible. Okay, so we would like to now summarize high channel mobile candidates. Gate capacitance and injection velocity are trade-off results in performance that is similar to silicon. Other materials like germanium and band structure engineering to increase the DOS without lowering the velocity should also is the research gap here. If one can implement these things, then it can be considered as a novelty. Then tunneling will increase leakage. This is the tunneling we are now talking about, the tunneling to the gate. Okay, so the gate tunneling is always a leakage. Band-to-band tunneling is required. Okay, so the importance of tunneling is actually through the band-to-band is shown here. When your gate length is 4 nanometer, 7 nanometer with respect to different technology nodes, 10 nanometer, and here is 13 nanometer, and so on. And this tunneling we see when it comes to the TFETs more in detail. Okay, so the next one is the nanowire FETs. This is another promising candidate for in place of conventional FETs. So as you could see here, CNT, carbon nanotube. Some of us have heard this name, right? It's like a graphene sheet, and this graphene sheet is rolled into a tube, carbon nanotube. We call that as a carbon nanotube. And the way in which you mold that into a tube, the chilarity of the tube also varies. And actually, carbon nanotube is a two-dimensional tube, right? So you have a normal longitudinal tube axis as well as chirality axis. So NA1 plus MA2, it's a two-dimensional array. Then N minus M is 3I, where I is the integer. Then it's metallic. If N is equals to M, is also metallic. In elsewhere, it becomes a semiconductor. So it's a complete research on its own. This CNT FET is carbon nanotube. So in nanowire FETs, a carbon nanotube is used in place of a conventional silicon, and you have a tremendous improvement in terms of the carrier movements like tunneling. And a simple gate cannot control in a nanowire FETs. You must have a GAA kind of gate all around, meaning to say throughout the tube you actually etch the gate layer. Then only we should be able to control the movement, because it's like almost near this moment, near ballistic moment. So here the layers are like close to the thing, and somewhere intermediate and somewhere bottom. So the tunneling is classified into different regions. One is IBT, okay, intra-band, like conventional valence band to conduction band, like the intra-band tunneling. Then band-to-band tunneling. Then HIBL, because of certain holes also, induced barrier lowering tunneling. And BT is the bottommost tunneling. So like that, they classify it. And we are mainly focusing on only IBT, intra-band tunneling. And the results are shown here by some research. And they are the benchmarks again. So why I'm showing certain results is, if you choose this candidate as your research field as a replacement for a conventional FET, then you must look into these benchmarks, and your outcome should be at least on par with this or beyond this. Then we can say we have done a considerable work in this field, like that. That is the reason why I have shown some, even though they do not actually show a complete explanation. Then imaginary band structure, for the sake of fulfilling a complete graph, they actually mirror the image here. So this part is actually imaginary, mirrored image. Same is the case, this part is the mirrored image. So the plot is actually only from this part. Then some other projections on nanowire FETs. So like that, nanowire FET is another promising candidate. As I said, in nanowire FET, GAA is required, gate all around, in order to control the movement of the carriers, because it's almost a near ballistic movement of the carriers from one end to another end, like a pool, like your tube, water tube, like water is flowing from one end to another end. So electrons are moving, in a near ballistic movement. So to control that movement, you must have a thoroughly controlled gate wrapped throughout the tube. How much effective width can be put into required gate pitch? These are all the considerations when you are looking into this area. Okay. Then Finfets compared with nanowires. Actually, nanowire is also quite good candidate. So they see silicon FinFET here, one fin and one nanowire GAA gate all around compared with that. Then 2 nanowire GAA, 3 nanowire GAA, and you can have multiples of that. Then we are moving on to the next one. Internal. Am I running out of time? Shall I continue? Okay, internal gain FETs. I CMOS. I CMOS is, as I said, internal gain MOSFETs. Okay, then in that there is one ferroelectric, right? FETs, and then some other NEM. This is actually going more towards the mechanical field. So here you have a negative capacitance as well. Why a negative capacitance? Ferroelectric. Why we are going for that is in order to have a negative capacitance as well. I will show you the reason for that. So as you see here, one is the entire MOSFET model can be classified into a combination of 2 series capacitances. One is at the insulator, at the interface. The other one is at the substrate. Okay, a combination of these two. So the total capacitance becomes series capacitance or a parallel combination, isn't it? C1, C2 by C1 plus C2, which is either less than C1 or less than C2. Okay. Now, in order to, if I can make this capacitance as variable, is it possible? Yes, that is possible to the ferroelectric. Okay, ferroelectric materials are used in order to have a variable substrate capacitance. Thereby, I can have certain say on the capacitance as well. Ferroelectric materials are used to do that. And some standard equations in order to, if you're interested in this domain, they are useful. And the observations are also shown here. And the energy band structure for ferroelectric materials. This is where we can see a negative capacitance. Okay, this one, if anyone is interested in this line, they can actually write to me. Like I said, in quantum mechanical effects, one is the DOS, density of states are not uniform. That's one of the quantum mechanical effects. And quantum reflections. Then another one is the conduction band is not uniform throughout the channel. Okay, the conduction band is actually conduction band edge is tilted at the surface. There are 2 types of things are available. Okay, this is one-dot model, they call it, and we have an approximation mathematical models for that. To what extent it's actually tilted at the interface. So that is why you see that it's tilted there, bend. And in some cases, we may have a floating metal gates as well. Okay, instead of using a metal gate, we can actually improve the performance of the capacitance. When I use a metal gate, it increases mass capacitance, uniform potential for each grain, and leakage paths, logic timings are the problems. Okay, so positives are these are the positives, and negatives are these are the negatives. So as I said, for each candidate, we have plus as well as minus. And again, when you are going for a ferroelectric materials to improve the capacitance of the gate and all those things, then you need to have a comparison to benchmark devices. And these are the benchmark devices, and it's a ferroelectric FET. Okay, Verilog models can be downloaded from this website, and the results can be compared with your findings in order to show that we have done a considerable amount of research. So this is another candidate. So the novelties are like novel device concept, potentially significant impact, encouraging results are emerging out because of these FETs. Significant challenges remain in terms of the materials. Okay, one has to do different material integration and intrinsic speed and reliability. And a lot of research is getting done at this moment only at the simulation level, not on the fab level. And the next one is TFETs, tunneling field effect transistors. Tunneling field effect transistors, actually, you have one combination of P, I, and N. Okay, P, I, and N. IN is the intrinsic semiconductor, P is the P-type semiconductor, and N is the N-type semiconductor. So here what we do is dopings varied. The valence band, when I apply the gate voltage at the gate terminal, the valence band and the conduction band of your valence band of your source and the conduction band of your intrinsic material, they come closer to each other. Then your electron tunnels to the band to panel. And if I reduce the voltage level at the gate, then again there is a gap between these levels. That can be actually shown here. So by applying the gate voltage, we bring this band closer so that the gate can, the carrier can tunnel to the band to band. So that's how the movement is. It's not because of no more like your conventional energy band diagram. It's actually tunneling to the band by controlling the gate voltage. That is the logic behind tunneling field effect transistors. And they are the quite promising candidates at the moment. Even the off state is quite good. Leakage currents can be minimized by using this. And some of the conventional, the benchmark models for emission models. All these are all tunneling field effect transistors outputs for on state as well as for off state. This is actually non-equilibrium green function simulations by using TCAT, okay, Silvaco TCAT simulations. And it shows a quite good, so that's why a lot of research is now going in the field of heterogate TFETs, because they seem to be more promising candidates. And the structure of this is shown here. One is PIN, that is the conventional method, and heterogate means I use a different material to design P, similarly to design N. Here I am using a 3-5, right? And here I am using also 3-5. Here is a 3-5. So in that way, TFETs are more prominent. Nanowire also is promising candidates. As I said, each candidate has certain pros as well as certain cons. Interesting device concept that could outperform subthreshold silicon CMOS in ultra powers. Okay, subthreshold slope is quite good in TFETs. Significant and growing body of experimental results, still looking for a breakthrough. Serious challenges must be addressed, like increasing on current without increasing leakage, scaling below 10 nanometers, maintaining subthreshold swing below 60 to higher currents. They are all some of the challenges. Okay, then two-dimensional channels are another ones. That is another promising candidate. Transition metal dihalogenate, TMED, in short we call it as MOS2. MOS2 means molybdenum disulfide, and WSET is like tungsten diselenide. These are the materials we use as a 2D semiconductors. They are quite ultra thin in terms of atomic scale channels and atomically smooth as well. No dangling bonds, stackable heterojunctions, uniform thickness can be achieved, mobility maintained through thin channels. All those things are, this is the general structure. Even I am not widely exposed into 2D TMD. My research is mainly towards TFETs and nanowire FETs. This is a relatively new field coming into where there is a good research gap. If one is interested, they can actually focus into this line as well. Okay, conventional as SI, double gate, and SOI, silicon on insulator. They are comparing the results with all these models and they outperform them. Okay, this is high performance and this is for low standby powers. Even the leakage are minimized. And effective mass, as I said, the carrier movement is actually reflected in terms of the effective mass movement in quantum mechanical models. Okay, so this is an excellent alternate candidate if you are looking for a research in this line. Result in ultra thin body and reasonably large effective mass, thereby your mobility, I mean, as well as your currents are higher. Double gate implementation is a challenge in this. Doping and contacts and mobility, etc. Device optimization is also a challenge. Actually, most of these candidates, even though you come up with some successful designs in terms of simulations, how far they are feasible in terms of fab designs, that is one challenge. Okay, so vertical TFETs, now we are looking into two-dimensional from TMEDs. Is it possible? Research can progress into this line? Is one of the active area now in the research. And some Atlas-based simulation models results are shown. As I said, they are quite challenging candidates, promising candidates as well. Okay, now I think we have seen quite a few alternate candidates and promising candidates in place of conventional MOSFET, like high channel mobility MOSFETs, nanowire FETs, internal gain FETs, TFETs, and 2D channel materials. As some of the promising candidates, we can focus any one in these and can benchmark the benchmarks shown in this seminar. If we can compare our results in our design with these benchmarks, then I can confirmly say that we have done a considerable amount of work in that line. And if you want to download the simulations, this is the site from where you can download. And summary is all device options face a similar set of challenges, right? Cost of fabrication, lithography. So that's the reason nowadays everything is on virtual fab, no more physical fabs. Increasing role of parasitics, okay, gate capacitance and series resistance, variability, electrostatics, and leakage, especially in tunneling. Difficulty of achieving desired ion-off ratio and reducing VDD. No device that's distinctly superior to silicon has been identified as on date. So silicon is still a possibility, but will it offer enough performance, okay, at 5 nanometer node and all. And as I said, right now, the 5 nanometer node implemented by Samsung and the TSMC is actually using a FinFET GAA gate all around and using SY technology. That is a combination of these three models. High mobility channels could work with careful considerations of trade-offs. Germanium MOSFETs, maybe ferroelectric mass FETs and TFETs and 2D metals is not ready for 5 nanometer mode development, but should be watched. Okay, beyond certainly not silicon anymore. Silicon is still somewhere there, but not completely on that. Electrostatic control will require nanowire or ultra-thin channels in DT architecture, double gate architecture. Leakage will be dominated by tunneling. And FETs, TFETs, and 2D metals could be the answer for that. Okay, so again, as I said, this is where we begin. We are ending the same way. And it's not until it's over. Okay, I think I'm open for any questions. I think I'm done. But each field, yes.
If anybody wants to ask any question, please raise your hand.
Okay, they can even mail me if they have time.
Yes. I request all the participants, if you have any questions, you can drop a mail to the sir's mail ID, and I will provide the mail ID. and or you can simply raise your hand so that we will unmute you. Once again, sir, Vikram Kumar. Sir, you are unmuted.
Sir, what can you throw light about the power dissipation problems? Because when the size is getting reduced, power dissipation come into picture. No, sir?
Yes. Actually, we are mainly looking for only the power dissipation part of it. See, when we are talking about when we are reducing the size, automatically the power dissipations are minimized, right? So all the candidates, what we discussed here, are ultimately contributing towards the power consumption.
Yeah.
We can have a detailed session on maybe once on power dissipation alone, where we can discuss about power delay product and multiplication of that. If the delay is minimized, power is minimized, PDP is automatically minimized. Thereby, for that we need to have a complete design on a model. Maybe we can go for an analog design or a digital design, maybe a full adder or a comparator. Then we can show more details on these power calculations. But all the candidates in today's seminar certainly contribute for minimum power consumption.
Yeah. Still, is there anyone who wants to speak with Ramana sir, or if you have any doubts regarding the session, you can raise your hand so that we will unmute you. Yeah, I think no one is having the doubts, sir.
Okay.
We can go with.
I thank all participants.
Yes.
And if you have even in future any interactions can be done through email. Okay. I would be happy to answer your questions. Thank you for your participation as well.
Vasumathi, ma'am.
Okay.
Yes, sir.
Ma'am, you can.
Gratitude is the most exquisite form of courtesy. I deem it great privilege to propose vote of thanks on this occasion. No event can take shape without a hard-working team. It is the collective effort of the convener, Professor K. Manoj Kumar, and the organizing committee which made this webinar possible. Their determination is praiseworthy. We extend our sincere thanks to all of them. I'm very happy to say that the experienced leadership and the unprecedented cooperation of our principal, Dr. R.V. Krishnaiah garu, in providing all the amenities made the hosting of this webinar memorable. We will ever remain grateful to you, sir. Most importantly, we would like to acknowledge our deep sense of gratitude to our esteemed speaker, Dr. Gajula Ramanamurthy garu, for his valuable time. Your years of research, your depth of understanding, and your ability to present the subject in such an interesting way resulted in one of the most memorable and knowledgeable evenings. The content you presented today will be echoed in our minds for a long time to come. I would like to take this opportunity to thank our director, Professor N. Venkatrao garu, for supporting us at every crucial juncture. We are also grateful to our Dean of Academics, Professor K. Venkatramaiah garu, and the HOD of ECE Department, Dr. N. Vijay Shankar garu, for their valuable suggestions. Furthermore, I would like to extend our thanks to Mr. V. Dinesh Babu from the Department of CSE for his cooperation and technical assistance. Finally, let us have a special recognition to all the participants from different states across the country for their active participation in the program. We hope that all the participants had an insightful and exuberant session. Thank you so much for your incredible support. Once again, I would like to state that we are most grateful to the eminent speaker of the program for enlightening us with his presentation. Before we wind up the session, on behalf of Chebrolu Engineering College, we sincerely promise you that in the coming days, we do keep organizing such proceedings to instill more knowledge and nourish your minds. We shall soon meet you in the virtual space with another webinar. Stay safe and stay healthy. Thank you very much.
Thank you.